Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. Although seemingly impossible, our mission is to transform some of that destructive hate energy into constructive love energy. Mathematics is part of all that surrounds us. Just pause and take a good look. As your screen suggests, like it or not, math really did take us from the Stone Age to the Space Age. The sermon is now over. Now let's get down to some serious math. This will be video 8 of the continuing video series in Algebra. And these are some random factoring problems that we're going to be going through. Because factoring is really key to solving problems in mathematics in general, so you've got to be fairly good at it. Otherwise, your career will be short-lived. Question 11a says, use all your ammunition to factor. Everything you've learned thus far about factoring, we have to apply it in order to factor the following problem. We have a 4x to the power of 4 minus 25x squared y squared plus 36y to the power of 4. We identified three terms. There's no GCF because 4, 25, and 36. There is no GCF, but that's the first thing we would look for. And if we look at x, the lowest power of x does not appear, and the lowest power of y does not appear everywhere. Okay, that y squared does not appear in the first term, therefore you can't factor it out. And that x squared does not appear in the last term, so you cannot factor it out. So there is no GCF, but we do recognize it as an HTF because the leading term over here, the x to the power of 4 term, has an a value of 4, which is not equal to 1. Okay, so we have an HTF problem on our hands. And it's of the form a dot x squared plus b dot x plus c. So let's see how this is going to work out. There's the problem again. That's just the header for the problem. We're going to put down the ABC chart right here. And of course, the ABC are just the quadratic coefficients, 4, negative 25, and 36. 4, negative 25, and 36. We write down all the numbers that multiply to give you 4, which are only 1 and 4. Actually, 1 and 4, and then 2 and 2. But it turns out that the 2 and 2 doesn't work, so I didn't even bother putting it down. And when you put down the numbers that multiply to give you 36, you have a bunch of numbers that multiply to give you 36, 1 and 36, 2 and 18. 3 and 12, etc., but the one that works out is just 4 and 9. You can experiment with the other ones, but they will not work out. So in this question over here, I just zeroed in on the ones I'll be needing. So I'll need 1 and 4, and I'll need 4 and 9. And the objective is to get minus 25. And let's try to do a parallel match. We get a 1.4, which is 4. And a 4.9, which is 36. No way to add or subtract 36 and 4 in order to get 25, so that's not a good match. Let's try a crisscross match. 1 times 9 is 9, 4 times 4 is 16. That looks like a good match. So we have 1 times 9 is 9, put it down. 4 times 4 is 16, put it down. We need to get negative 25 when we add up these two numbers, so it must be a minus, because minus 9 minus 16 will give you a negative 25. And then don't forget to verify. A negative times a negative will give you a positive, which carries the same sign as C. So we know we're on the right track, and we boxed in the correct factors. Okay. So in the next step over here, just open up an empty bin. You'll recall that we did a crisscross match. We did 1.9, which is 9, and 4.4, which is 16. So when we put the numbers down, it will be a parallel. Okay, so we have a two-variable form. Now, instead of putting xy down here, it's going to be the square root of x to the power 4, which is x squared, and the square root of y to the power 4, which is y squared. Okay, so then we get 1 dot x squared and then 4 dot y squared, and we put it down here. We get 4 dot x squared and 9 dot y squared, and we put it down here. Recall we did a crisscross in order to get 9 and 16. Therefore, we're going to do a parallel now, which is the opposite to put the numbers down properly. We're going to do 1, 4, 4, 9. So we get 1 dot x squared, 4 dot y squared, 4 dot x squared, 9 dot y squared. So that goes into the first set of brackets, and then 4 dot x squared, 9 dot y squared goes into the second set of brackets. And then leave the signs out. Always leave the signs out. Now we're going to do an inside-outside to get the correct signs. 4y, we're going to do the inside first. 4 dot y, if 4 dot 4 is 16, we need minus. So we put a minus sign there. And then over here, a 1 dot 9 will give you 9, and we need a minus sign there. So there's the minus sign there, and the other minus sign there. Now, if we look at this carefully, we'll see a difference of squares. And this is also a difference of squares. So we're going to use DOS factoring here and DOS factoring here simultaneously. All I did was copy paste, write it down again, and I call this DDoS for a double DOS. Okay, so over here the square root of x squared is x, put it down. The square root of 4 is 2, put it down. The square root of y squared is y, put it down. And then you have x2y, put a minus and a plus for the DOS factoring. Similarly, over here, the square root of 4 is 2, put it down. The square root of x squared is x, put it down. Square root of 9 is 3, put it down. Square root of y squared is y, put it down. So copy paste 2x, 3y, 2x, 3y, and put a minus sign and a plus sign. We have linear factors right across the board, and therefore we are done. We have the factored form at the end. Okay, so this is an example of a double DOS problem. Let's go on to the next slide. Question 11D. Again, it's an all ammunition problem. So we're going to have to use all of our resources to do it. I notice that we have 2 terms and only 2 terms. I notice a minus sign in between. I notice even powers for the variables. And I notice that 16 and 65, 61 are both perfect squares. Okay, so I notice 2 terms. There's minus sign in between. There's no GCF. And we definitely have a DOS on our hands. So we're going to use the DOS formula. The square root of 16 is 4. The square root of x to the power 4 is x squared. Square root of 65, 61 is 81. Square root of y to the power 12 is just y to the power 6. So you copy 4x squared, 81x to the power 6, and just copy it down again. You put a minus sign there and a plus sign there for DOS factoring. Now, if you examine the first factor over here, 4 is a perfect square, 81 is a perfect square, x squared is a perfect square, and so is y to the power 6. So we have another DOS on our hands over here. On the other hand, these are all perfect squares as well, except we have a plus sign, so we have a sum of squares. A sum of squares has the form a squared plus b squared, and it's always a DNF. DNF means does not factor. So don't bother trying to factor the SOS, which is sum of squares, but we can factor the DOS, which is a difference of squares. So this guy gets dropped down, goes along for the ride, and we're going to apply another DOS factoring to this one over here. The square root of 4 is 2, the square root of x squared is x, the square root of 81 is 9, the square root of y to the power 6 is y cubed. Copy paste again into the second bracket, and put a minus sign there and a plus sign there, and the DOS is over. This cannot be factored anymore. This can't be factored anymore. And of course, this is sum of squares, which cannot be factored. So the factoring is complete. We're done. That's a factored form. Okay, so let's go on to the next slide. Again, it's a use all ammunition problem. If we look at this carefully over here, we have 1, 2, 3, 4 terms. If you recall, a 4-term factoring problem indicates that we probably have a factor by grouping problem on our hands. Okay? The thing is, in the last few problems that we did on factor by grouping, we acknowledged having 4 terms, but we would group the first 2 terms and the last 2 terms together. This problem over here is a little bit different, so look out for a problem like this. Over here, you'll notice we have an a squared term, an a dot b term, which is a cross term, and a b squared. The 9c squared, I call it the oddball term. That's the term that's by itself. It has nothing to do with a and b. Therefore, what we're going to do is group 1 is going to be the first 3 terms, and group 2 is going to be the last term, or L1. First 3 and the last 1 term. That's how we're going to do this kind of grouping. So again, to group, all you do is insert a pair of brackets, drop down the first 3 terms, that's all I did, and then the minus sign I'm going to leave outside. And I'm going to put the 9c squared on the inside because I think it looks like I might have a difference of squares on my hands. Okay, this is certainly a perfect square, 9c squared. If I can show that this quadratic, like a 2-variable quadratic term over here is in fact a perfect square, then we're in business. Okay? And this over here looks like an HTF problem in 2 variables. It's HTF, 2 variables. But now I'm allowing you to do the HTF on your own on the side so you can get some practice. We've already done quite a few HTF problems, so I'll leave it up to you. It turns out that the HTF factoring goes 2a minus 3b and 2a minus 3b again. Of course, an apple times an apple is just an apple squared, so we have a perfect square on our hands, and then we have minus a banana squared. So we have something like a dot a, which is a squared, and then we have minus b squared. So apple squared minus banana squared. Group 1 is a perfect square, and of course group 2 is also a perfect square. And in the next step, we acknowledge that by writing bracket 2a minus 3b all squared, perfect square, minus bracket 3c all squared, also a perfect square. And now we simply use DOS factoring to complete the problem. And to use DOS factoring, we take square roots. The square root of the first term is just 2a minus 3b. The square root of the second term is just 3c. Disregard the sign for now. So you have 2a minus 3b blank 3c. All you do is copy paste into the next set of brackets. So you get 2a minus 3b blank 3c. And then you put a minus sign and a plus sign because that's what we do when we do DOS factoring. DOS factoring is of the form a minus b, a plus b. So they're conjugate pairs multiplying each other. And this is a linear factor in a, b, and c. This is also linear in a, b, and c. So this will be the final factored form. Okay, so we'll go on to the next slide. And we'll call it quits because I think we're done with the algebra series. And so this will be the end of the algebra series, and thanks to all for viewing this video series. Stay tuned for many more videos to come. If you liked the video, please give us a like, submit, comments, and subscribe to our channel. If not, please tell us how to improve it. Over and out from Math Lab Tutorials in Toronto.